Alright, so let's get started with the case setup. Now you can click on begin case setup, and this basically helps you get like a wizard like structure which you can follow so that you can set up your simulation. So in this case we are going to be using the general flow option, and let's click on apply and done. Now here you can see that these are the different things that you need to set up, like materials, simulation parameters, boundary conditions, physical models, and so on. So the first thing that I'm going to do is, in this case I'm interested in running like a laminar flow simulation. So what I can do is, first I can go to materials, and you can see that I need only gas, but I don't need any reaction mechanisms because I'm not simulating combustion here. So let's just unselect that, and the predefined mixture is going to be air, and click on apply. And when you do that, Converge basically says, hey, do you want to go with air as the predefined mixture and you want to overwrite gas.dat, mech.dat, and therm.dat? Yes, we do. So let's just click on yes and then click on done. Similarly, we don't need a turbulence model because this is going to be a laminar flow. So I'm going to click on physical models, and I'm going to just uncheck turbulence modeling, click on apply, click on done. Now any other parameter that you want to set up or explore, you can just click on the headings. For example, when you click on simulation parameters, if you want to include body forces, which is gravity, you can check this. In this case we are not going to do that. Now you can see that run parameters, simulation parameters, and solver parameters have been checked, and this has been grayed out. Why is that? Well, these are default fields, they will never go. So for example, if you just hover on this, you will see that this option is required and is always active, right? So there's nothing you can do about these guys. So let's just click on done. Alright, so now the idea is very simple. We are just going to work our way from top to bottom to set up the simulation. So global transport properties, I'm just going to click on OK, and I'm using the default values. For run parameters, we are going to be using a pressure based steady solver. Let's click on OK, and then we are going to accept the default tolerances and relaxations. Let's click on yes for this also, and then we're done with it. For simulation time parameters, we are going to start with 0 cycles. We are going to end at 15,000 cycles. And we are going to basically start at 1e minus 9. That's going to be the starting time step. 1e minus 9 is the minimum time step, and 1 is the maximum time step as well. So let's click on OK, and then for solver parameters we are just going to click OK. Then comes your boundary. So here we are going to say at the inlet we are going to be having an inflow boundary. It's a total pressure inlet where the pressure is going to be 1 Pascal more than 1 bar. So it's going to be 1 followed by 4 zeros, and there's going to be another 1, right? And air is going to be the incoming fluid. And then at the outlet we are going to be using a static pressure outlet. So let's select outflow, and here you can see that the pressure is 0 Pascal. We are just going to say that this is 1 bar. Alright, so make sure that you're inputting this correctly. Sometimes we have seen that people accidentally put one additional 0 and the flow starts to reverse. Make sure that you don't do this. Species backflow. If your outlet pressure is higher than the inner cell temperature, then the flow can actually reverse. If the flow reverses, then it's going to come in at 300 Kelvin, and the incoming fluid is also going to be air. Top and bottom walls, well, they are just going to be walls, and what we are basically saying that this is just going to be a no slip wall. And for temperature, we are just going to say that it's a specified value, which means it's a fixed temperature or a Dirichlet boundary condition, and the value is 300 Kelvin, and we are going to click on OK. So what we are doing here is we are just setting up the flow simulation. I understand that there are so many things that might not make sense. So initially, the reason why we are doing this is to make sure that we are able to get from the simulation start to the simulation end, which is basically post-processing and all that stuff. And since there are so many softwares in play, I want to make sure that you guys are able to run everything perfectly, and that is why we are just taking up a very simple test case and we are following through. At this point, please don't worry if you are unable to understand what a particular option means. These are things that you will be learning throughout the course. So you can see that now on boundary there are several errors, right? So we will try to identify each and every of these error. We will try to understand what these errors mean, and we will try to propose a solution. But for now, I'm just going to move to regions and initialization. So remember, initially we had triangles and we grouped the triangles to form boundaries. Now we need to group the boundaries to form volumetric zones, which are called as regions. So I'm going to create a new region, and I'm going to say that it contains air, but then I'm just going to mix or basically reverse the concentration. Why is that? Well, this should be fairly clear to you when you actually see the simulation results. So I just want you to trust me at this point and put this number, and when we are post processing it, I'll explain to you why we are doing this. Now this is not the concentration of air. Air contains 77% nitrogen. However, here I've said that air contains 77% oxygen, which is just the reverse of it. But there is a good reason why I'm doing this. And you need to remember this term initial conditions, because I'll be making a reference to that later. So let me click on OK here. So at this point, turbulence modeling is not required. I'm not sure why it appeared again. So let me click on apply and let's click on done, right? So now let me click on boundary again, right click and validate. Now you can see that you have the same errors. So it says undef underscore region, which basically says undefined region. It says boundary 1 is not assigned to a region. Well, what it means is, you have all your boundaries, which is your inlets, outlets and all that stuff, but they are not assigned to a volumetric region. Well, they need to be, right? I'm going to select this guy and I'm going to select region 0. But what is region 0? Well, if you're not sure, don't do this. Close this guy, go to regions and initialization, and this is region 0. You can right click or you can use F2 to rename this, and I'm just going to call this as volumetric region, right? And I'm just going to be really verbose and say this is user defined and click on OK. Alright, so now let me go to boundary and double click on region undefined. You have this option. Right, I'm just going to go ahead and select all of them, and I'm going to put them in this particular volumetric region, and I'm going to click on OK. So now if you right click and click on validate, boom, most of the errors are gone. You have only 2 errors. So let's click on this guy. You can see that the front and back, they have not been assigned a boundary type. So let me click on front 2D and say that this is a 2D boundary, and back 2D is again a 2D boundary. Now let's click on OK, and then comes your base grid option, right? So this is basically your computational mesh. Now before we do this, I want to just put the geometry in this particular view so that we know that the flow goes from left to right. And I'm going to go to options, and I'm going to go to visibility, and I'm going to enable geometry bounding box so that I understand the size of the model, right? So let's click on base grid. So here it's basically asking me for a mesh size along X, Y and Z direction. Now along X is the longest dimension, right? So we have about 0.1 meters. So I'm going to say that, well, you know what, I need like maybe 100 points. So I'll just say 0.001. So basically we are saying that every 0.001 meters or every 1 millimeter, we are basically going to have like a computational cell, actually half of that. So this is basically going to result in 100 cells along the x-axis, and along the y-axis I'm going to go for say 10 cells at least. Why? Well, we know that in these type of duct flows there is a velocity profile, right, which looks parabolic, and in general any gap that you have, you need to have at least 5 to 6 cells to capture the velocity profile accurately. So in this particular case, along y-axis, the dimension is 0.01. So if I need 10 cells, well, that's going to be 0.001 as well, correct? So that's going to give me 10 cells, and along the z-axis I really don't care, because that's the direction in which the flow is going to be ignored, in other words made 2D, right? So let's just click on OK now. So that way base grid has also been checked. Now let's look at post variables and selection. What does this mean? Well, these are the quantities that would be output in a 3D format. So when we are doing the post processing, you would be able to visualize all these quantities. In general, you can see the density, pressure, temperature have been selected. For this exercise, go with the default selection, except click on species, and what I want you to do is I want you to click on mass fractions, and what we're going to do is we're going to select N2, we're going to press add, and we're going to select O2 and we're going to press add. Oops, so I don't think I need this one, so let's delete it and click on OK. And for output files, what we are going to do is we are going to select an interval. So you can see that the time interval for writing 3D output is currently 1000 cycles. So every 1000th time step I have one output file. Now remember, I'm running the simulation for 15,000 cycles, which means I have only 15 outputs. That seems a bit less to me, so I'm going to modify this to 100 and I'm going to click on OK. That's basically it. So now at this point we have set up the simulation, but how do I run this? Well, that is where you need to understand the role of Converge Studio. Converge Studio is setting up the simulation, and when I'm saying setting up simulations, it's basically helping us to create certain input files. What do I mean by that? So let me actually click on boundary here, right? So when you do this, you have this graphical user interface, so where you're selecting the different boundary condition. Actually what's happening behind the scenes is Converge takes the data that you're inputting using your mouse and keyboard, and it's creating a text file. And if you don't believe me, click on the second button on the bottom left and you will see something called as export preview with a name of a file, boundary.in. Well, this particular graphical user interface is being used to write that file. So for example, if you look at this, you can see that one inlet, inflow, velocity, pressure, and you have this value, right? So the graphical user interface, whatever options that you're putting, depending upon the type of options, Converge Studio at the backend is creating this input file. So technically you can directly edit this input file, but you need to understand the format. For example, when the pressure is inside a square bracket, that means it's total pressure, and there's no way for us to understand that. And that is why there is a graphical user interface, because it helps you generate that and it gives you an intuitive interface. So this is something that you need to remember. Similarly, if you click on regions and initialization and click on this preview button, here you can see that export preview says it's initialize.in. That is the name of the file. And here you can see that there are so many variables, and you can see that there is a variable value and there is a variable name. Now this is the name that Converge uses behind the scene in its computer code, right? So this is really important, guys, because at the end of the day, Converge Studio is not basically running the simulation directly. It's first creating the input files, which can then be used to run the simulation. So how many files are there in total? Well, depending upon the simulation, it varies. But to get a good sense, you can go to File, Export, and export input files. And you see that 1, 2, 3, 4, 5, 6, 7, 8. There are 8 files in total for this particular case. Now there are situations where the number of input files goes up to 30 and above, right? So those would be really complex simulations. So what do I do after this? Well, I can take these data files. Let me just go to a folder where I can run some simulations, and I'm just going to go to my support folder, which is in Converge runs support, and I'm going to call this as channel test, and I'm going to select this folder and I'm going to click on OK. When you do this, you can see that 8 files have been exported in total. Awesome. So what do we do after this? Well, now that we have all the files, we need to run it. And in order for us to run this, we need an executable, and that is where the second file comes into play, which is the Converge 2.3.26 msmpi win64.exe. This is what you call as a solver file. This is different from Converge Studio. Both of them are executables, but this runs the simulation, whereas Converge Studio helps you just set up the input files. Okay. Now a little comment about the name. It says Converge 2.3.26. Well, 2.3.26 is the build version. So 2.3 is the major version, 0.26 is the build, right? What does MSMPI mean? Well, that means that this Converge executable supports the MSMPI parallel architecture, which means you can use this to basically run simulations using multiple cores that is available on your laptop or desktop. And then this is a Windows 64-bit build. All right. So this is what we are going to be using. So the next thing that you need to do is you need to download this. All right. You can see that the file size is about 7 MB. Now, before we are able to use this particular file, we need to download a program called Sigin. Sigin basically offers a command line interface which helps us run this simulation. Now you can actually use your Windows command prompt to do the same thing, but it's not at all efficient. So in the next video, I'm going to teach you how to install Sigin and how to use it. All right, I'll see you in the next one. Bye.